right, so we're going to begin by talking about just some examples of polynomial functions. So as an example, f of x is equal to 3x to the fifth plus 2x to the fourth plus x to the third plus x squared plus 5, right? Polynomial functions look super nasty and big, and we're just like, geez, man, what do we do with all this information, all right? But there's a couple of pieces that I want to get out of here that I want to introduce you to. First of all, each of these things right here, this piece, this piece, this piece, this piece, and this piece, these are each called terms. All right? So we call those terms. So how many terms does this piece polynomial have? 5. Yeah, this has 5 terms altogether, right? There are 5 terms in this case. And in this case, the leading coefficient is the number that's right in front of the highest degrees term. So we call this thing the leading coefficient.
Is it the largest coefficient or the one with the number with the
Yeah, so that leads me into the next part, right? So we're talking about, so far we have terms, we have leading coefficient, and then we have what's known as the degree of a polynomial. And the degree of a polynomial is the highest exponent's value. So this is a 5th degree polynomial. So we have degree, we have terms, and we have leading coefficient. These are the 3 important parts in talking about a polynomial. All right? So let me give you another example. f of x is equal to 7x to the 4th plus 2x plus 5. All right. What would you call this polynomial if I asked you to give me its name by degree? What would the degree of this polynomial be? Yeah, this would be a 4th degree polynomial, right? Now, how many terms does it have? 3. 1, 2, 3. Yeah, we call those trinomials, right? We talked about that before. So this is a 4th degree trinomial. Easy enough. And what's the leading coefficient of this 4th degree trinomial? 7. It's a 7. There you go. And that's my leading coefficient. All right. So you feeling pretty good so far about what a polynomial function is? Okay. It's important that our exponents be integers, like 5, 4, 3, 2, 1. We don't want any exponents of like 2/3 or pi or anything like that. So make sure that our exponents are integers, and pretty much where we're going to focus our thoughts for today. So the second idea here, I want to talk about behavior slashed with notation. Okay. So what I want you to do is I want you to give yourself 4 quadrant planes here, 4 little mini sketches here. 1, 2, 3, and 4. And we're going to talk about all possibilities of what these graphs could be doing, what these polynomial functions could be doing. So let me give you an example of one, right? I could have a polynomial that does this. All right? Or I could have a polynomial that kind of does this, in this kind of general direction. Or I might have a polynomial that does something like this. Or I might even have a polynomial that bounces around and does something like this. But the important part here is that the end behavior of our graph is doing something. I'm talking about the end behavior of our graphs here, right? So we have certain ways that we can describe this so that it makes sense when we're talking in generalities here. And the way that we describe it is a 2-part step. So what we say is, for the right-hand side here, we could say, as x values go to positive infinity. So what do I mean by that? As x goes to infinity. That means that as my x values start to increase in size without bound, what does the function f of x, which is represented by this red line here, where does the function end up go? It goes to infinity. Very good. So that means that f of x goes to positive infinity. And that's a statement that we can make using this type of notation. So as x goes to infinity, f of x goes to positive infinity. So we're saying as x gets unbounded, our function is also unbounded. Now, could I make another statement for the left-hand side of this graph here? We could say as x goes to where? Where is x going? Where are my x values going? Very good. Negative infinity. What's f of x doing? F of x is going to negative infinity. Very good. All right, let's see if we can make up some statements for this one on the right-hand side. As x approaches what value? No, on the right-hand side here. Positive infinity. Where's my function going? F of x goes to negative infinity. Very good. What about this one? As x approaches negative infinity, where's f of x going? Positive infinity. Very good. All right, could you fill in the other two, do you think? Okay, in your table groups right now, fill in the other two graphs for the left. All right. Okay, so I want to make sure that everyone realized that the actual red graph was f of x. Okay, I'm not sure that maybe you guys didn't catch that, but it seems like everyone was on track here. So the one on the left here, Amy, what did you get for as x goes for this one on the left here, this bottom left one? Yeah. Mm-hmm. As x goes to negative infinity, f of x goes to positive infinity. What did you put for the right-hand side here? Mm-hmm. Good. As x goes to infinity, f of x goes to positive infinity. And then, Ryan, what did you get for the right-hand behavior on the one on the right here?
As x goes to infinity,
Yep.
x goes to negative.
Very good. And then on the left-hand side, what did you get? Mm-hmm.
Okay, as x goes to negative infinity, f of x goes to negative infinity.
All right, good. Did we miss any? Are there any other possible combinations here of a left and a right-hand behavior? Nope. That looks like all of them, right? So here's what I want you to do now, all right? In your table groups, I want you to take a look at these three examples of polynomial functions. And what I want you to do is I'd like you to graph each of these three functions in the same viewing window of your calculator. And I would like you to look for patterns and look for behavior. And I want you to talk about it within your group, okay? You're looking for patterns and behavior. Okay, so what everyone is telling me here is that all of these graphs here, they all kind of behave the same way. You guys told me that they kind of match this first one here, where they go down the left and then up on the right. And that's kind of what they do. Now, they do some funky stuff in between. Like this blue one is pretty extreme, and this green one's kind of not so extreme. But the end behavior, right, as x goes to negative infinity, f of x goes to negative infinity. And as x goes to positive infinity, f of x goes to positive infinity. So there's something going on here that allows all of these to sort of do what they do in terms of end behavior. And we kind of agreed that these kind of go, we said it goes down on the left, and then up on the right. Does you agree with that? Down, left, and up, right? Okay. Now, I'm curious, though. Does anybody notice anything that's in particular about these three polynomial functions? Bobby, what do you see?
I see that the higher the degree of the second term, the more extreme.
Oh, he says the higher the degree of the second term, the more extreme and stuff here?
The less extreme.
Less extreme? Okay, I agree. Yeah, what do you think?
All the degrees are odd.
All the degrees are odd. Look at that. All the degrees are odd. That's interesting. What else do you notice? Yes?
The degree that's like in with the leading coefficient is bigger than
The leading coefficient.
like the 3 times that is always bigger. Like
Oh, okay, you're saying it's bigger than the second term. Okay, that's a good thing to notice. What else do you notice? Yes?
The higher the degree of the first term, the less extreme.
Okay. What about these first coefficients here? 2, 5, 10. Anybody know anything about them? Yeah.
2 times 5 equals 10.
Good. 2 times 5 equals 10. Yeah, that's true. Does that have anything to do with this? They're multiples of 10. 2 is not a multiple of 10. They're all what type of numbers? They're all positive, right? They're all positive, okay? Yeah, they're all positive, okay. All right, here's what you do. Take a look at these ones now. I want you to graph these on your graphing calculator next. Yeah, so when we graph all of these in the calculator, okay, we're noticing that they look an awful lot like the second one over here, right? They sort of rise on the left and fall on the right, okay? So I wonder if there's any connection here. What do you notice about their degrees?
They're the same.
No, they're not. They're the same.
No, that's the ones before.
Are they odd or even?
They're negative.
Their degrees are odd, but their leading coefficients are now what? Negative, so we get this type of behavior, right? So we say this is up, left, down, right. Okay, there's a connection here between all these things, okay? Okay, we'll do these ones together. What do you notice about all of these right here?
They're all even.
Their degrees are even and their coefficients are what?
Positive.
Positive. So if you had to guess, what do you think the end behavior is going to be if, given the fact that we've already seen left on the right and rise on the right?
I have to guess it's the W.
What do you think?
The W.
The W? All right, let's see. That's the wrong one.
I guess the W.
All right, so if we graph all these, check it out. What are each of these doing?
They're like they're not
Okay, remember, we're only concerned with end behavior, right? We're concerned with the end behavior. So as x gets really, really big or really, really small, they're not all parabolas. Only one of them is a parabola, right?
They're all U.
The one that's not what?
Okay, what I'm looking for here is
Quadratic function.
okay, some just any old generic polynomial function, x to the n. We kind of have four cases that we can talk about here, all right? So if n is odd and a is less than 1, or n could be odd and a is greater than 1, or n is even and a is greater than 1, and the last one, n is even but a is less than 1. Okay, so which of these, for n being odd and a was less than 1, let's see, let's go back over here, okay, or the second ones here. Check it out. N is odd, our exponent is odd, our coefficients are less than 1. What's the end behavior here? So, down on the right. This one we're going to up on the left, down right. Up, left, down, right. Okay. If n was odd but a was greater than 1, such as these first ones that we had, n is odd, so our exponent is odd, but our a value is greater than 1, looks like, how would you describe their end behavior? Down, left, up, right. All right. Down, left, up, right. Does that make sense? Yeah. Okay, what about n is even but a is greater than 1? What do we got? Let's see here. Even, greater than 1. So there it was like that. Even and positive looks like they're both up, right? Okay. Up. If n is even but a is less than 1, well, we kind of did some investigating here, and looks like it's down, left, and down, right. So this is going to be right. All right, so this is our leading coefficient test. So let me give you some examples. You guys tell me, what is the end behavior of the graph going to do according to the leading coefficient test? So what if I gave you f of x was equal to negative x cubed plus 4x? Okay, how can we describe what this graph's going to look like before we even graph it? Well, I know I have a negative a and I have an odd exponent. So n is odd and negative. This has to be going up on the left and down on the right. Does that make sense? So if I were to actually graph this thing, negative x cubed plus 4x, over here, if I said y equals negative x cubed plus 4x, here we go. We're going to say it's going to go, look at that, up on the left, down on the right. Is that what we predicted? Yep, pretty cool, huh? Up on the left, down on the right. That's exactly what it says right there. Up on the left, down on the right. Pretty cool, right? Okay, let me give you another one here. Predict what this one's going to be. If I gave you f of x was equal to, how about x to the fourth minus 5x squared plus 4? What is that one going to be doing in terms of end behavior? Well, yeah, we have a positive a and we have an even degree. So even and positive looks like up on the left, up on the right. So if I was going to graph this, the end behavior as x approached positive and negative infinity, our function would also approach positive and negative infinity. Pretty cool. All right? So right now, I want you to create a polynomial function that will go down on the left. And so if we graph all of these, check this out. Check this out. These are all behaving in the same way. All the ones that you guys came up with, they go down on the left and down on the right. So we could say, as x approaches positive infinity, f of x goes to negative infinity. And likewise, as x approaches negative infinity, f of x approaches negative infinity as well. Okay, you guys feeling pretty good about this today? Hello? You guys good?